Hello and welcome to the Power and Considerations for Passive Optical LAN webinar presented by the Association for Passive Optical LAN. My name is Dave Cunningham, the chairman of the board for the Association for Passive Optical LAN, and we got a great lineup for you today, some great information about how to handle remote powering in a passive optical LAN environment. First, we have Jamil Kantouk, a senior marketing manager from Nokia. He will cover the considerations for electronics and POL, particularly how to the powering requirements for ONTs. We have Kevin Borders, Vice President of Marketing with Alpha Technologies, and he'll give us some different techniques that you have and options that you have for both local and remote power. And then Scott Fitzgerald, a senior engineer and manager of product management with Optical Cable Corporation, and some design of the optical network and how to handle designing the infrastructure to make it efficient and handle the remote powering needs that you're going to have. And then we'll follow up with a question and answer session. So if you have questions throughout the webinar, please feel free to use the Q&A tab and enter your question there. We'll get those lined up for the end of the webinar and answer as many as we can as time permits. So I appreciate everyone's attendance, and we'll start with just a brief introduction of the Association for Passive Optical LAN, give you an update on what our purpose and mission is. The Association for Passive Optical LAN was created 3 or 4 years ago, and our mission is really to educate and advocate passive optical LAN adoption in the local area network marketplace. And we came together as a nonprofit trade organization, and we've got manufacturers, distributors, integrators, consultants who are all actively involved in this POL marketplace. And if you think about some of the names on this list, the founding members across the top and the other members who have joined since the founding of the company, we've got a great group of big names in the industry who are all behind passive optical LAN as a technology and who have helped grow this industry to what it is today. And it's exciting to see the growth that we have in the Association for Passive Optical LAN. And if you're interested in joining the Association for Passive Optical LAN as a manufacturer or distributor or a company who works in the passive optical LAN space, you can always check APOLANglobal.org and get the ways to sign up there. But a great list of companies who are behind this technology, and you're hearing from some of them today on this webinar. In 2017, we've got numerous companies joining all the time. We're seeing growth in both Europe and our European committee, but also the launching of an Asia Pacific committee who extends the outreach of the Association for Passive Optical LAN to a global outreach. We have a growing social media community, people following us. We're both on Twitter and LinkedIn, so you have at APOLAN Global on Twitter, and you can search for APOLAN on LinkedIn to find us there. Follow us there for news and updates. We've got an email that you can sign up for, educating more than 1,000 people, and we're constantly working with news organizations on articles. We're presenting webinars like you're going to see today, as well as news releases on events in the passive optical LAN industry that are noteworthy. We've got an online readership of over 2 million for those different vehicles. And we also actively participate with organizations such as VIXI, other organizations in the network technology industry to help train professionals in passive optical LAN. We've done that. Over 300 professionals have been trained through the VIXI program that we have, and actually gaining valuable continuing education credits for those. So again, if you're interested in joining, follow us on social media, check out the website, apolanglobal.org, with all the information there, and you can see all the great things going on in the organization. And really just a brief setup on for those of you who may not be familiar with what a passive optical LAN is. On the left-hand side of the screen, you'll see basically a traditional local area network. And in traditional local area networks, which is where I spent a lot of my career building and designing local area networks, you have layers of electronics in the network that do the centralized routing and switching functions, and then you have the distribution layer, and then out to the access layer of the network where you actually are connecting devices. And every one of those layers has their own set of electronic switches in the aggregation layer at the core of the building, communication closets within 300 feet of every device that needs to be connected. And these closets and these aggregation points are often difficult to maintain. They have a lot of cable entry coming into those areas, and a lot of power requirements, which introduces cooling requirements, as well as the security challenges you have in maintaining control over those devices sitting out in that environment, and knowing who's entering the communication closet when they're leaving, what was done while they were in there, those kind of things. And all of these challenges have led to the adoption of passive optical LAN in several different industries. And what's different about a passive optical LAN is that you start with the same campus aggregation type of environment with a core switch called an optical line terminal, OLT. And that OLT and the entire rest of the network is all centrally managed and provisioned via an interface designed to completely manage and give you visibility into the entire network. There aren't other ways to manage the network. That is how the management gets done. And it gives you a lot of flexibility in managing and seeing what's going on in the network. But the other large difference is what happens below that campus aggregation layer on the right-hand side at the building aggregation and the communications closet layers. You'll see there aren't actually electronic devices there. Those are actually optical splitters, and you have a wide distance because this is an optical-based solution using single-mode fiber and splitters to do the distribution of the signal. The middle of the network in a passive optical LAN is passive. There's not electronics involved, which gives you a lot of flexibility in where those splitters can be located. Instead of building a closet in your business for housing electronics and powering them and cooling them and securing them, everything that goes into that, you instead can just put these splitters where necessary in an environment. And we'll talk more about how the power would flow through in this presentation today. At the other end of the network, out at the edge where your devices need to connect, you have what's called an ONT, an optical network terminal. And that provides you the ability to switch from the fiber signal over to a standard Ethernet signal. And that Ethernet signal allows you to connect any type of Ethernet device. And these devices could be anything from thermostats and wireless access points to computers, video surveillance cameras, all your type of audio-visual and menu boards, and all the things you would see connected to a traditional network. So it's very easy to implement, takes a lot of complexity out of the middle of the network, and gives you centralized administration. So as we start to think about that end device, the ONT, that device is a power device, and it needs obviously needs power to operate. And so as we start to think about powering that device, which is the focus of today's webinar, I did want to have a quick poll question that we can answer before our first speaker. And that is, you'll see that up on the screen now, and I'd like you to vote on this poll question. How frequently do your installations require a battery backup? And so when you're working in a local area network environment, how often do you have to have power backup in that environment in case of a power outage? So I'll let you guys go ahead and cast your vote, and we'll continue as soon as we get some poll responses in. So while we're waiting for the poll responses to come in, our next speaker will be Jamil Kenturk, and he's going to talk about powering considerations and for passive optical LAN. And I'm going to go ahead and push out the poll results so we can review those right before we go to Jamil. So the poll results are less than 20% of the 25% of the time, 17%, but the majority, 51% of the time, or 51% of the respondents said that they have the requirement for battery backup more than 75% of the time. So I appreciate your feedback on the poll. And now we'll introduce Jamil. And Jamil, you can take it away with your part of the presentation.
Okay, thank you, Dave. A warm welcome to everyone, and thank you for joining us here today. I'm Jamil Kanturk. I'm responsible for Passive Optical LAN marketing at Nokia, and I'm also a member of the APOLAN marketing committee. Today, I will be talking about the powering considerations for the electronics in a Passive Optical LAN, and in particular the ONTs. So I'll give an overview of what is local and remote powering of ONTs. Okay, so let's start with local powering of ONTs with AC power. So in the main telecom room, you have the OLT, which is equipped with a dual or which is equipped with a redundant power feed. The single mode fiber and passive splitters make up the infrastructure. And finally, you have the ONT that is providing connection to the endpoint devices. In this case, the ONTs are powered with AC power from a local AC power, via a separate power supply unit. The physical dimensions of this power supply unit is comparable to that of a laptop, for example. Powering ONTs with AC power is used in indoor deployments and is actually addressing applications, or most applications in enterprises, hospitality, educational institutions, by utilizing the same electrical outlets provided at the endpoint device. For example, a workstation or a PC in an office. Another option of local powering of ONT is with a battery backup. So the Passive Optical LAN network configuration is the same as on the previous slide, but in this case, the ONTs are equipped with a battery backup to prevent network connectivity losses during a power outage. Now, the backup time is typically between 30 minutes and 120 minutes, so enough of time to allow maintenance staff to detect the power outage and to switch to a standby power generator system. Again, it's mainly used in indoor deployments and is actually addressing applications where the power service is known to be unreliable or where the application is a mission-critical operation, for example, a call center. The typical guidance is to provide a battery backup whenever the application itself is also on a battery backup. Okay. The pros and cons of local powering of ONT. Well, on the pro side, it delivers on the benefits of Passive Optical LAN with a true passive and fiber infrastructure. There are no active elements between the OLT and ONT, so there are no failure points in the midspan. The reach is unaffected, so one can still cover distances up to 20 kilometers. And although powering with AC power addresses most applications, in some cases a battery backup may be required. On the con side, so both powering with AC power and battery backup limit the ONT location placement, so the ONT needs to be in close proximity of a power outlet. The battery backup unit is a separate device, and which can actually increase the complexity of managing the network. And then we have the limited lifespan of batteries, which may require regular replacement of the batteries. Okay, an alternative, or the alternative to local powering is remote powering of ONTs. So deploying Wi-Fi access points or high-definition cameras or any other device, especially in outdoor conditions or in outdoor environments, it can be difficult. It can be difficult, especially to find a local power source, for example, on the sides of buildings or on poles or on lampposts. Okay. Yeah. Okay. So the alternative is to remotely power the ONT through a remote power distribution unit. So in this case, so the Passive Optical LAN network or the POL network configuration differs from the ones on the previous slides because we are introducing a new element, and because of the fact that the passive infrastructure is no longer purely passive. So between the remote or between the power distribution and the ONTs, the cabling is a combination of fiber for the data and copper for the power. So the power distribution unit is 1 unit high, 19-inch rack mountable device with 32 ports, providing 48 volts DC towards the ONTs. It's co-located with the passive splitters, and you also have a variant which is actually combining the two boxes or the two devices into a single box. A UPS needs to be installed together with the power distribution unit, or the combination of the power distribution unit and passive splitter can be placed in the same room as the OLT. Then the power distribution unit can be sourced from the same UPS that is powering the OLT. All right. So the pros and cons of remotely powering ONTs. Well, it consists of a centrally located UPS, which actually eliminates the need for local power sources at each endpoint device location. Where available, the legacy copper cabling can be reused to power the ONTs. And the key benefit of remotely powering ONTs is that it allows to place the endpoint devices exactly where they are needed. On the con side, it reduces the value proposition of Passive Optical LAN with a less passive infrastructure and increased maintenance. The cabling infrastructure or the footprint is significantly higher and more expensive, and there are not many power distribution vendors on the market, and one must be ready for the potential for problems with electrical permits. To summarize, what stands out in the case of local powering of ONTs is that it's truly passive, and the fiber runs from the OLT all the way to the ONT with no failure points in the midspan because there are no active elements between the OLT and the ONT, and it addresses most, if not all, indoor applications. Concerning remote powering of ONTs, well, the Passive Optical LAN value proposition is reduced with less passive infrastructures, but on the other hand, it allows to place the endpoint devices exactly where they are needed, and typical use cases are deployments both indoor and outdoor where there's no local power available. Okay, so I've been talking about the different powering options of ONT, so I wanted to share a couple of examples with you. On the left-hand side, you have a typical POL ONT with 4 GG ports and PoE support and a battery backup. On the right-hand side, you have the combination of passive splitters and power distribution units. And the top picture, for example, is an integrated passive splitter and power distribution unit. And this brings me to the end of my presentation. So back to you, Dave.
Thank you, Jamil. That's a great presentation on the use cases for ONTs. And now I'd like to bring up our next poll question. How many of your endpoints require a backup when you're creating a local area network design? How many of the endpoints actually require backup power as an option? So your options there are very few, some, most, or all. We'll give a few minutes for those to fill up. And while you're filling out the survey, I'll also ask you to make sure to get your questions entered into the Q&A functionality of the presenter here so that you can make sure we get to your questions during the Q&A period. And if you have a question, drop it in there. We'll try to prioritize them as best we can and get them answered. So the quicker you get them in, the more time we have to evaluate and prioritize them. So let's take a look at what we've got here. I appreciate those of you who have answered the poll question. Looks like that most people chose most with 39.1%, and then pretty much a relatively even split among the other three. So thank you for your feedback on that. And now we're going to go to Kevin Borders with Alpha Technologies, Vice President of Marketing, and he's going to give us an overview of local and remote line power. So Kevin, take it away.
Thanks, Dave. For those of you who don't know Alpha Technologies has been in the industry for 40 years. We design, manufacture, and install AC and DC power equipment for a variety of industries, including cable TV, telecom, wireline, wireless, traffic intersections, and enterprise. We're a member of APOLAN, and I serve on the technology committee for APOLAN as well. I've been with the company 6 years and in the industry for 35 years. So Jamil covered local and remote line power use cases. What I'm going to do is give you a quick review of local power and then do a deeper dive into the remote line power solution. And the reason is local power is traditional. It's fairly well understood. It requires an AC outlet at every ONT, whether it's powered with a wall ward or whether you need a UPS for battery backup. This does complicate things because it requires you to maintain the batteries at the end of your network. And the other issue with local power that comes up sometimes is that the power connections are accessible to the public. This can also be an issue in the case of, say, hospitality, like a hotel room or in a school. So let's dive deeper now into the remote line power topic. So with remote line power, the power source is actually centralized. So you can see in the diagram there's AC that comes into an AC to DC rectifier. That rectifier connects to a DC-DC converter, which has some special current limiting capabilities in it. And what you end up with is a circuit that meets NEC Class 2 for safety and fire prevention. And that device actually powers the ONTs using copper cable that runs alongside the fiber that you're installing. Typically what we've seen is that you need 18 gauge, occasionally larger, but usually 18 gauge to power the ONTs. So let me explain how it works in sort of simple terms. AC will come into the power configuration. It comes into the rectifier. The AC is converted to DC, which is a nominal 48 volts. There are battery strings that are in parallel with the rectifier to provide backup for all the circuits that are connected to it. This rectifier and battery combination powers a special DC-DC converter. The DC-DC converter has current limiting capabilities built into it for distributing the current over copper to multiple ONTs. The current limiting capabilities are provided to ensure that you have no more than 100 VA or 100 watts on any circuit, and that's for safety considerations. The other thing the DC-DC converter does is it increases the voltage from a nominal 48 volts to 57 volts. And that becomes important, we'll see later on, to ensure that you have enough voltage to power PoE devices at the end of the circuit. The other thing is that the 57 volts is a constant output and will be there as long as you have power to the source, whether the power is a rectifier or whether it's on battery backup. And it'll be a constant 57 volts, which means you can plan your network using 57 volts as your standard output. So I mentioned NEC Class 2 circuits. The National Electrical Code, and this applies actually in the U.S. and in Canada, defines a certain type of indoor remote power circuits. And the Class 2 circuits are considered safe from a fire initiation standpoint, and they also provide acceptable protection from electrical shock. So what that means is that if you install these Class 2 circuits, you don't have to worry about them causing a fire or somebody being hurt by the circuit. The benefit of the Class 2 circuits, financial benefits, is that they can be installed using conventional surface-mounted cable. So that means you don't have to have conduit or armored cable. They can also be installed by your installers, your regular installers. You don't require an electrician to certify the installation. There are three main attributes of an NEC Class 2 circuit. The first is that the voltage must be less than 60 volts DC. That's the official term is safety extra low voltage limit. So it's less than 60 volts, which, as I mentioned, the DC-DC converters output 57 volts. The power has to be limited to 100 watts or 100 VA per circuit, which is what these special DC-DC converters do. Then the third thing is that the power limit must be maintained even when a primary protection device fails. Now, this is an important clause because it, in effect, eliminates the use of fuse panels in a Class 2 circuit. And here's why. A fuse panel, which you're familiar with, you have a 48-volt input from a rectifier, and say you use a 2-amp fuse. So you could argue that, well, 48 volts times 2 amps is 96 watts, therefore I meet the standard. However, the standard requires you to meet that even when the fuse, which is the primary protection device, has failed, when it is not operating correctly. And you cannot guarantee then that you'll meet a 100-watt limit. So consequently, fuse panels aren't really available for use in Class 2 circuits, although there have been some that have been installed simply because people were not totally aware of the NEC. A common question we get asked is, how far can you go with remote line power? You're powering over copper cables, so how far can I reach? And the way we do this is we start at the end device and work backwards. So many ONTs can source PoE power. So we assume a 50-volt minimum coming out of the ONT. We also know from experience that ONTs often will have a 1-volt voltage drop across them. So that means that the input of the ONT needs to be 51 volts. Now, I mentioned earlier that the output of this DC-DC converter is 57 volts, which means you have 6 volts available in voltage drop across your copper cables. Now, if you look at the table, what you see is the load, which is the amount of power consumption by the ONT on the left-hand column. And then as you go across the other columns, they show different gauges of cable. And all of those numbers then will be in feet. So if we're taking a typical example of a 70-watt ONT, and that would be one that is able to provide power for the PoE devices, you can see that using 18-gauge cable, you can actually go 275 feet. That is typically more than enough for the applications that we have experience with, although there may be some outliers where you have to go further, and you can see that if you went to 16-gauge cable, you could go to 450 feet. So this just gives you a basic idea of how far you can reach. It's going to vary based on the ONT. It's going to vary based on not only the ONT manufacturer, but also whether it's a single-port or 4-port ONT, and whether or not you're powering PoE devices. So with remote line power, there's really two different major design options. The first option I'll talk about is whether you distribute the DC equipment near the down converter, near the DC-DC converter, and near the ONTs. So what you see in this example is on the second floor, that's supposed to be a cutaway of a building. So on the second floor, you see a combination or a configuration of a rectifier and battery that connects to a device. This is our E-limiter plus, which is the DC-DC converter. And coming out of that DC-DC converter, you can actually power multiple ONTs. There's several cable pairs that come out of that. Most installations that we've seen, they locate those devices on a floor and then serve a floor above and a floor below. That minimizes the amount of space that's required in your intermediate distribution frames. So in this example, you see the power equipment located on the second floor and also on the fifth floor. So the second floor serves floors 1, 2, 3, and the fifth floor configuration serves 4, 5, and 6. You have AC that comes into the building, and the AC is actually in the riser and goes up to the second floor and up to the fifth floor, and there's separate AC circuits required for each of those rectifiers. The pros and cons are illustrated here. All of the cabling is going to be NEC Class 2 compliant. So all the cabling on the floors, you can use surface-mounted cable and your own installers, which is going to reduce your installation cost and your equipment cost. On the negative side, you have to have space in your IDFs for power equipment. You also have batteries in the power equipment room, or in the IDF. And so that means that you have some amount of battery maintenance that has to take place where it's not centralized, but it's actually distributed throughout the building in certain locations. This also requires multiple AC circuits because each rectifier requires its own AC input. Now let's look at an alternative solution, and that's the centralized option. The centralized option, you take the rectifier and battery combination and you locate it on the first floor or maybe in the basement, and you run out of that DC power, DC cable that goes up and powers the same configuration that we had in the previous slide, where you have the DC-DC converters on a floor serving 2 other floors. And so the difference between the one I just showed you with the distributed plants and the centralized plants is that in this case you have DC in the riser. Now, there's pros and cons again with this one as well. You have a single DC plant and a single set of batteries. So maintaining the batteries is very straightforward, very simple, and you're also doing it in an equipment room. It also requires less space per floor for power equipment because you don't have that on the second floor and the fifth floor. All you have is the limiter plus device. The downside is that the cabling cost to run these Class 1 circuits or in the DC circuits up to each of the DC-DC converters can be expensive depending on the situation or the facility's characteristics. It can require conduit, an electrician, and depending on how big the load is and the distance from the power source, it may require larger gauge cable. The DC plant and the battery system are also larger in order to account for the converters and the distance. So either option can be applied. It's going to depend really on the site characteristics. So let me recap what we just talked about. Local and remote line power are both viable options for power and POL. It really depends on the specifics of your site. Now, remote line power is somewhat new to the POL world, but it uses a technique that's been used for a long time in powering broadband, fiber to the home, distributed antenna systems by both wireline and wireless carriers. There's cost advantages for remote line power versus local power. And there's also cost advantages for distributed versus centralized architecture, but it's all going to be dependent on the specific site characteristics. We've had many options and many opportunities where we've installed equipment where the remote line power was the winner in the both CapEx and OpEx analysis. And we've used both distributed and centralized architectures, again, based on the application. Then lastly, the centralized nature of remote line power means that you have fewer locations where you have power and fewer locations where you have batteries. And what that does is actually increases the reliability of your network. And as I mentioned earlier, can also guarantee that you have battery backup for all the circuits in your network. So thanks, and with that, I'll turn it back over to Dave.
All right, thanks, Kevin. That was a great presentation on that section. And I want to bring up the next poll question. So if possible, if you have an existing implementation, would you consider reusing the existing category cable for powering the POL circuit? So reuse the cabling that's already there to power the circuits. And you have three options there. The yes, it would save me the expense of purchasing new cable. No, I use the old cat cable as a cable puller or a cable string for the new cables, or not sure. And so I'll give you a few seconds to answer that question. And while you're answering that question, I will say that if you want a download copy of today's presentation, you can do that using the Download Slides widget. It's the green widget in the bar across the bottom of your browser there. So if you want to go ahead and download those slides will be available for you. And let's check and see what results we have. Thank you for everybody who participated in the poll. Looks like pretty fairly split. You know that about 40% would consider doing that, 35% unsure, and 25% would use the old category cable as a pull string for the new cables. So thank you for your participation in that poll. Now we're going to go to Scott Fitzgerald from Optical Cable Corporation, and he's going to give us the infrastructure considerations. So we talked about powering and the ONTs themselves, and now let's look at the impact on cabling infrastructure with Scott.
Thank you very much. My name is Scott Fitzgerald. I'm a senior engineer and also the manager of product management for Optical Cable Corporation. Optical Cable Corporation is coming up on our 35th anniversary of being in the fiber optic cable industry. And today I'm going to talk to you about infrastructure considerations and cabling infrastructure considerations for specifically for remotely powered passive optical LAN installations. Key considerations, and we'll go into each of these in more depth: wire size and how that affects voltage drop, fiber count and type, whether you want buffered fiber or subunits in your cable, flame ratings, fiber and wire management, and connections to the ONT. We've talked already about wire size, and Kevin mentioned that 18 gauge is a fairly common size based on the distance that you need to carry power. Copper wire's current carrying capacity is a function of the cross-sectional area, and that can either be measured in millimeters squared or in AWG, just depending on which country you're in. Here in the U.S., we refer to AWG, or gauge. As you can see in the picture on the right-hand side, though, there is a correlation between gauge and the size of the wire. It's actually inverse, so a 16-gauge wire is significantly larger cross-section than a 22-gauge wire does. Because of that, the 16-gauge wire will have a lower resistance than the 22-gauge wire, and that will be important later on. As we've already discussed, your power distribution network needs to be able to provide proper operating voltage to your ONTs, and typically that's going to mean no more than a 6-volt drop over the length of the cable. As I just mentioned, larger gauge, larger cross-sectional area wires have a lower resistance and therefore will have a lower voltage drop in terms of volts per meter at a constant operating load. So the power to your ONT devices the power to power over Ethernet devices connected to your ONTs must be considered. For example, your ONT may draw 15 watts, but if it's powering 4 PoE devices at 15 watts each, then your overall power draw is 75 watts. And that 75 watt number is the number that needs to be considered when doing your power and distance calculations. So truly, the PoE devices connected to your ONT, they can draw much more power than the ONT itself. Now let's talk about fiber count and type. A passive optical LAN only requires a single fiber to carry bidirectional data, and that's one of the advantages of a passive optical LAN. However, it may be smart to include a second fiber in the cable as well. The incremental material cost is low compared to the cost of having to replace a cable if you have a problem with a fiber. And this way you can have either a spare fiber that's dark, or you have other options later on for future growth. There are multiple versions of single-mode fibers that are available on the market. The standards that govern the bend insensitivity of the fibers are G.657.A1, G.657.A2, and G.657.B3. As you can see on the diagram on the right, each incrementing standard has a tighter and tighter bend radius that the fiber can be bent into and not have excessive optical loss. But one thing you need to keep in mind is the extra bend insensitivity of G.657.B3 may not be needed if you include that fiber in a cable with large copper conductors, because the overall cable probably can't bend tight enough to exceed the G.657.A1 standard. So that's an area where you can save money by using a slightly less bend insensitive fiber compared to other types of installations. The next thing you need to consider is, in terms of a cable construction, is do you want buffered fibers or subunits? One common design on the left uses 1 or 2 900 micron buffered fibers cabled with 2 copper conductors. The alternate design on the right has those same 900 micron buffered fibers contained within a 2.0 millimeter subunit, and then those subunits are cabled with the copper conductors. Both of these will typically have aramid yarns for tensile strength. And down at the bottom, we really show the key advantage of each design. On the left, with no subunits, you have a smaller OD, outer diameter, and on the right, you provide better protection for the fibers. And each of these has their own use within your network. Let's talk a little bit about flame ratings. I'm going to have to stay a little bit vague here because I know there are attendees from all over the world. We are located in the U.S. and I'm most familiar with those standards. In the United States, riser and plenum are 2 grades of flame ratings that are required when your building may be subjected to a building fire. But obviously, you need to be paying attention to your local building codes and laws. In the U.S., powered passive optical LAN cables are most likely to be run through plenum spaces, and so most installations will buy a plenum-rated cable. But again, you need to check with your local building codes and make sure you're following your local laws, regardless of what jurisdiction or country you're in. Another design attribute that you need to take into account is fiber and wire management, specifically back at the splitter location. At the splitter location, you're going to have many fibers and many copper wires that are going to need to be properly terminated and managed. There are a lot of products out on the market that will help with this, but to give you a sense of the magnitude of scope, a 32-way splitter is going to have up to 64 wires and 32 or possibly even 64 fibers that need to be organized, managed, and not damaged. So it's a tremendous amount of wire and fiber that needs to be organized, and the fiber and wire management piece does not need to be or cannot be overlooked. Next, I'm going to talk about ONT connections and actually making the data connection to your ONT, the fiber connection. Most ONTs use an SC APC connector for the fiber connection. This is where the ferrule is beveled at a 7.5-degree angle to minimize back reflection. The SC APC connectors that you use must be compatible with the cable you chose. So you'll recall a few slides ago we talked about 900 micron buffered versus a 2.0 millimeter subunit cable. The 900 micron buffered fiber cable is best suited for protected environments, such as when your ONT is located inside of a wall cabinet or a wall box or a secured cabinet away from the public. And for those, you will need SC APC connectors that are designed to mate to the 900 micron buffered fiber. 2 millimeter subunits are best suited for exposed environments where the ONT is accessible to the public. And there, the subunit and the layer of aramid surrounding the 900 micron buffered fiber provide extra protection for that fiber. And the connector itself will actually crimp onto the aramid, allowing the aramid to serve as a strength member. We also need to think about the copper connection to the ONT. And this is going to vary by ONT manufacturer, but I've put here some common techniques. One style is the Phoenix style connector, which is that green block. The nice thing about these connectors is they don't require specialized tooling. They just require a screwdriver to terminate. Other ONTs may use a 5.5 millimeter coaxial DC jack. Typically, this is the same plug that's used for local powering using a wall wart. In this case, you will need to mount or terminate a 5.5 millimeter coaxial plug onto the wires in your cable. This may require a specialized crimper or a soldering iron. Not necessarily specialized tooling, but certainly more than just a screwdriver. And there are many other power connection options, and this is going to vary by the ONT that you choose for your network. It's important that you figure this out early in the planning phases so that you can make sure that you've got the right connectors and the right cable and that everything is compatible with each other. Similarly, back at the power distribution hub, where you have your power distribution set up, you're going to have 32 pairs of wires that are going to need to be connected to that hub and using some form of a connector. And again, that's going to vary by which power distribution hub you choose. In summary, there are a lot of design considerations that need to be taken into account when designing a remotely powered passive optical LAN infrastructure. The key things that we've discussed here today that you need to keep in mind are wire size, the copper connections, the fiber count and type, the fiber connections, what flame ratings are required by your locality, and wire and fiber management. And as we've mentioned before, and as has been evident through some of the other presentations today, when remotely powering your ONTs, the voltage drop on the power conductors is going to limit your maximum cable length long before the fiber optics ever will. And this is a change from typical passive optical LAN networks that can typically go 20 kilometers. Some of the numbers that Kevin presented, your powering options may only go 400 or 275 feet, depending on the load and the wire size that you choose. So therefore, your copper infrastructure choices are just as critical to the success of your network as are your fiber choices. And Dave, I'll turn it back over to you. Thank you.
All right. Thank you, Scott. So we've had three separate kind of discussions around the ONT considerations, the powering itself and how that is designed and happens, and then the cabling and how the infrastructure would lay into a remote powering or powering scenario. So let's go to our last poll question of the day. And the question is, are you planning or would you use a separate category cable for remote power for your ONTs, or does the single mode fiber composite cable with fiber and copper in the same cable, would you prefer to use that, or would you use a hybrid of both? And while you're answering those questions, I'll again remind you that the presentation's available. You can get there via the download slides widget, green bar at the bottom of your screen, of your window. And then we'll begin with your questions in just a second after we get the poll results in. So if you have a Q&A question you would like us to try to address, we've got quite a list. And we'll spend the last 10 minutes here getting to as many as we can. So thank you for submitting your answers on the poll. So we'll look at the poll results here. Looks like the composite cable is a very desirable option for a lot of you. And a hybrid of both, based on the situation, would be the second place result there. And then Category X cable, Cat 5, 6, et cetera, would be the third choice. All right, so we're going to move to our question and answer phase. Thank you for participating in the polls. And we have just about 9 minutes left in our webinar. So we're going to have our presenters answer some questions that you guys have submitted. So I'm going to start with, let's look at the list here. Got a question from, or a question for Kevin. The central DC power could also be a single point of failure. Is it possible that the entire network can go down in a centralized DC power scenario?
That could happen, but typically what you have when you centralize the power is you have multiple layers of redundancy. So your rectifiers will usually be deployed with an N+1 redundant arrangement, which means if one of the rectifiers fails, you still have enough power coming out of the rectifier bank. The second thing is that your batteries are typically deployed with multiple battery strings. And when you do that, you have parallel battery strings so that any one battery failure will not cause an outage. So if you lose AC power, or if you lose a rectifier, you could have a problem. Or if the rectifier itself, if the system had a problem, it could create a situation. But you have batteries to back you up. Now, the batteries are only going to last for a certain amount of time, and that's going to be dependent on how long you choose to equip them. So it may be 2 hours or 4 hours or 8 hours of backup. In most cases, that gives you ample time to provide a generator, whether it's a standby generator, which would be on present, or a portable generator. So, yes, a centralized plant could take down the network, but it would be a rare condition. And the best example to compare that to would be a central office, which are sort of bedrock. They very, very seldom fail because of power.
All right. Thanks, Kevin. I've got a question here on also, I guess, for you, Kevin. Can you talk about the HVAC requirements for the DC to DC converter and what the impact on the room cooling would be there?
It is a consideration. It's going to vary based on the amount of DC power that you have at the site. And you also have to be sure that your equipment room either has AC or is well ventilated, because the devices themselves can operate over a fairly wide range, as can the battery. But it is a consideration. I don't have really specifics for you because it's going to vary based on the size of the load, the size of the room it's located in. But you typically need some level of airflow, whether it's fans or HVAC.
All right, great. Question for Jamil. What's the typical backup time of a battery backup for an ONT?
Yes, okay, thank you, Dave. During my presentation, I gave the example of a typical backup time between 30 minutes and 2 hours. But of course, one can provide a backup times of 4 hours and even 8 hours. It really depends on the power consumption of the ONT and the number of batteries that you are using.
Okay. All right. And then a question here for Scott. If if a larger size wire carries more current, why not just always use the largest size wires?
That's a good question, and there are a couple of reasons. The first reason is price. A significant portion of the price of a hybrid cable or even a standard power cable is the cost of copper, which fluctuates daily. Larger gauge wires will have more copper and thus will cost more. They'll also be heavier. But you can typically find a balance. It may be advantageous from a bulk purchasing standpoint to use, say, 18 gauge throughout a project rather than buying 18 and 20 and 22 that's sized exactly to each run. So it may be advantageous from a bulk purchasing standpoint, but at the end of the day, you still need to consider the price and the cost of having all that extra copper in your network.
All right, great. And Kevin, a few questions. So we have several questions on both using up-down DC voltage converters as well as digital power. So could you give a brief explanation of how those could fit into a remote powering scenario? The up-down DC voltage converters like are used in fiber to the home, and then digital power, which has recently come on the market.
Well, there's a couple of considerations with digital power in these applications. And basically what the digital power does is it converts the 48 volts into an elevated voltage, transports it over the cable pair or the copper wire, and then down converts it back to a voltage that's usable by the ONT, just to sort of set the stage. One of the issues with that is that it drives up your costs because now you have a down converter at every ONT. And the second part of this is that you have to place that down converter somewhere near the ONT. So it not only increases the cost, but also increases the complexity of the installation. If you use something that has a 57 volts, while the distance reach isn't quite as long, you can actually run the wiring behind the walls and connect to an ONT that, say, mounts in a standard game box, and you have nothing to see. There's nothing there at all. So the other thing about digital power is the jury's out on how you comply with the National Electrical Code on that, because the voltage is significantly higher than the 60 volts. So do you have to put it in a conduit? There's some debate about that. If you do, obviously that's going to blow your cost model up.
Okay. All right, thanks for that. Just a few housekeeping notes here. I did have one question on will this be recorded? And yes, a recorded version of this webinar will be available. Also, if you would like, and we will email that out to the participants as well as the broader list for people who could not make the webinar today. Also, if you want the slides from today's webinar, there's a download slides widget in green at the bottom of your page. And then also, if you are interested in more information on the Association for Passive Optical LAN or would like to consider joining the Association for Passive Optical LAN, you can go to APOLAN Global, APOLAN global.org, and find more information there, as well as following us on Twitter and LinkedIn. We have time for just a few more questions, so let me scroll through here. We have a question on if I have dedicated circuits, and let's see, Scott or Kevin. Kevin, why don't you talk to this one? The advantage of not installing AC circuits everywhere you have an ONT. Can you compare the advantages or the disadvantages of AC power everywhere you need it as opposed to DC power, low voltage? Well, one of the disadvantages of having AC power at the ONT is that you have to dedicate an outlet for it, and depends on whether the outlet's available. If it's a new building, do you spring for the cost of the outlet? The other thing I mentioned in the presentation is that when you use local AC power sources,
you'll have something plugged into them, like a wallboard. And that's accessible, typically accessible to the public. Now, if it's an enterprise, an office building, that may not be a big deal. But if you're in a hotel or a classroom or someplace where you have the general public, then it can be a big deal because take a hotel room, somebody unplugs the device so that they can charge their phone or use something there, and what you end up with is you lose your service. So that's one of the issues. The cost analysis between DC and AC is really driven by the site characteristics, and so it's going to vary based on the site, whether it's a new install or existing, and basically the size of the facility, etc.
Okay. All right. Well, we are out of time for today's webinar, but I want to thank all of you for attending the webinar. I want to thank our presenters for their knowledge and sharing their experience and their expertise with us. And if you'd like more information about the Association for Passive Optical LAN, please check out our website at apolanglobal.org. All right. Thanks, everyone, and I hope the rest of your day is just great.